Hi, my name is Chris Foote. I'd like to welcome everyone to today's NoSQL Architectures presentation. We'll be uploading a copy of the presentation to SlideShare tomorrow morning. All participants will be sent a follow-up email that includes a link that will allow you to download a copy. By default, GoToWebinar mutes all participants except the speaker, which is a good thing because it reduces the chance of background noise affecting the presentation. We're going to hold questions until the end. There is a button on the GoToWebinar panel that will allow you to type your questions in. Kelly, who's the webinar's organizer, will bundle them up and we'll discuss them at the end. We want to be respectful of your time. We know that many of you will have meetings right after this one. We've timed the presentation to allow a Q&A at the end, but if we are in danger of running over, I can always respond to any remaining questions by email. Our intent is to have these RDX Insights presentations monthly. If you have suggestions for a future presentation, just send an email to cfoot@rdx.com. I'll display my email on the last slide of the presentation. Next month's presentation will be Choosing Cloud DBMS Architectures. We'll discuss the different types of cloud offerings, Infrastructure as a Service, IaaS, Database Platform as a Service, DBPaaS, and hybrids. We'll then take a look at some of the more popular IaaS and DBPaaS alternatives. I'll also provide a set of questions each shop needs to answer to determine what's the most important to them when evaluating cloud systems. We'll also review a starter set of criteria we can use to evaluate the various cloud offerings. I also distribute a monthly newsletter you might be interested in. It covers interesting technical topics that we think would benefit our customers both personally and professionally. This month's newsletter includes articles on Is NoSQL the Natural Progression of Database Technology?, a link to a video presentation on cloud's hidden impact on IT shops, SQL Server on Linux, and the rise of DB ransomware, holding your databases hostage. Each newsletter also has a helpful hint on how to maximize your relationship with RDX. If you'd like to be added to that distribution list, let me know. You can also add me as your LinkedIn buddy. I write articles and SlideShare presentations on a lot of different wide-ranging technical topics. So let's get started with today's presentation. It's challenging to collectively analyze NoSQL architectures as a group because their storage models are so dramatically different. NoSQL databases are currently thought to be most appropriate for special purpose implementations. In NoSQL's case, those special purposes include storing semi- and non-structured data, as well as accommodating large amounts of information and high numbers of concurrent users. Each of the storage models that we'll be discussing varies according to the vendor. The NoSQL vendors began by initially leveraging the open source version of the database software and then made it their own by adding additional bells and whistles to the base product. The longer the vendor is in business, the more bells and whistles you'll find. Their modifications range the spectrum, from monitoring and administration tools to simple database mechanisms. In addition, the NoSQL vendors also offer the added benefit of 24/7 problem support and software updates, fixes, patches, point upgrades, major software releases. The systems we'll be reviewing today are Document, MongoDB, Graph, Neo4j, In-Memory, Redis, and Key Value, also Redis. Redis is an in-memory data store, but it stores its data on disk, its persistent database in a key value format, and wide column, which is Cassandra. I purposely did not include Hadoop as a product because it is not defined as a database management system in the classic sense. Although it is available to interact with databases, it's really a file system, not a DBMS. One of the leading adoption drivers for NoSQL architectures is their ability to easily store and process unstructured data. We're no longer just storing text in our systems. Images, videos, sensor data, email chains, system logs, drawings, geospatial, all of it unstructured. Not only do we need to store this data, we need to turn it into actionable insight. Raw data provides no benefit until it's transformed into meaningful information that is purposely designed to facilitate better business decisions. Third-party vendors have identified the IT community's increasing interest in unstructured data and are marketing products that fill in those gaps. NoSQL database systems allow us to store the data, and there's an increasing number of analysis tool vendors that have offerings that provide the analysis capabilities. You have vendors like Tableau, SAP, IBM, Microsoft, TIBCO for BI. Other tool providers, monitoring, security, auditing, they're also modifying their products to ensure compatibility with these NoSQL systems. In my next slide, let's take a look at an example of a modern application and the type of data it displays. Here are some industry forecasts on the growth of unstructured data. IDG, unstructured data is growing at the rate of 62% per year, and by 2022, 93% of all data in the digital universe is going to be unstructured. Gartner, data volume is to grow 800% over the next 5 years, and 80% of that data will be unstructured. The industry forecasts show that as IT professionals, we are going to have to contend with an exponentially increasing amount of unstructured data. So why is unstructured data growing faster than structured? It's because application needs are changing. Here's an example of what the NoSQL vendors describe as a modern application. The application displays relationship data, geospatial, images, videos, audio. These unstructured data types historically have not been easily stored in relational rows and tables. One of the additional benefits of NoSQL architectures is their ability to scale horizontally as well as vertically. We've been able to horizontally scale our middle tier, our web service, for some time now. In order to accommodate increased demand, we just injected additional servers into that middle tier. But database servers present more of a challenge. While traditional database clustering has been available from the industry heavyweights for years, it's both costly and complex to administer. Compare the cost and complexity of an Oracle RAC or SQL Server always on, to MongoDB's sharded environment or a Cassandra cluster. MongoDB and Cassandra offer the capability to easily scale our systems horizontally, using architectures that are more cost-effective and more easily administered than RAC or always on. Instead of the more traditional approach of increasing capacity by opening up the chassis to add CPU, memory, disk, or migrating that database to a hardware platform that has more horsepower, these NoSQL architectures provide us with the ability to easily and cost-effectively scale our systems horizontally. I had the good fortune of working with the first commercially viable releases of both IBM DB2 and Oracle. At BNY Mellon, I was a member of a team that built one of the first large-scale financial applications on IBM's relational platform. Other more conservative members of our organization would tell us that the relational model was just a flash in the pan and that would never gain widespread adoption. Relational databases would be relegated to niche implementations. Like any new product, DB2 didn't have a robust feature set in its initial releases, but it did offer increased flexibility, reduced application development times, and was able to store many more different types of data. I was told no features, no future. When I began supporting Oracle, I was astounded at the benefits this new upstart product provided. It could run anywhere, as it didn't need a mainframe. The ability to run on low-cost commodity hardware, reduce support requirements, and the product's flexibility were the primary driving factors for Oracle's increasing popularity at that time. But I received the same comments about Oracle as I did for DB2, no features, no future. I think we can draw a correlation between the initial implementation of relational systems and their NoSQL counterparts. As NoSQL matures and new features are added that allow it to be more universally implemented, it's a relatively safe assumption that it will follow the same natural path as its relational counterpart. When we evaluate NoSQL offerings, we need to compare them against a standard. The standard in this case is relational database management systems. The two most common transaction consistency models are known by the acronyms ACID and BASE. Most relational databases use ACID, and their NoSQL counterparts, depending on the product, can use either BASE or ACID. What these acronyms mean is, can you really trust your data to be there? Most of us are familiar with ACID transactions from working with relational databases. This is what we're used to working with. ACID has several properties. One of them means that once your transaction is complete, you can trust that your data is consistent and it's on disk. Some of the other ACID properties are one transaction doesn't contend with another. that your unit of work is either, all of that work is either applied or rolled back. But in this case, we're going to talk about ACID versus base when it comes to data consistency between replicated nodes. A base data store values availability, since that's what's important for scale, but it doesn't offer guaranteed consistency of replicated data at write time. The key word for this discussion is that replicated data. Think of it this way: ACID is instant consistency for your data across all replicated nodes, and base is eventual consistency across all replicated nodes. Eric Brewer, a professor at Berkeley, wrote a paper that defined the CAP theorem for large-scale distributed systems. In the upper right, we see a graphic portraying a fully multi-master clustered system, meaning that any client can read and write from any node. There are three definitions we need to learn to discuss the CAP theorem. Consistency: all the servers in our distributed environment have the same data at the same time. Availability: the system is there. It's going to generate some kind of response to the calling application. And partition: it's just a high-tech term meaning a network connectivity loss. It prevents our two servers, in my example here, from communicating. To simplify our discussion, we've built a two-node cluster. It shares data over our network. By replicating it, we are allowing users to update that data on both nodes, both sides. If we lose the connectivity between the two servers, a partition occurs. And now we only have really two choices. We can choose availability over consistency, which means we still allow both sets of users to access and update the data on their server. Since they are now interacting with data that is no longer being replicated or synchronized due to our network failure, they could be acting on data that isn't current. It could be a classic business decision, a shopping cart, for example. You may want to take the chance of not having a product in stock that the user thought you had, but the overriding business need was that the user should be able to continue because you don't want to prevent the bulk of customers from being able to purchase goods by making their system unavailable. You want to take the smaller risk of not having that product in stock. If we choose consistency, we could identify one of the servers as a statement of record and make the other system unavailable. We could be sure that if the data is, it's only updated on one server, that data is going to be consistent and current. But the other set of users will be out of luck until synchronization becomes available again. In relational systems, they will always choose consistency. Let's take a look at our first product. It's a document data store called MongoDB. Why did RDX choose MongoDB to provide a service offering for this product? One of the more important evaluation criteria RDX used to determine which product we would support is the potential scope of application. Was the vendor's technology able to support a wide variety of applications? We wanted to select a robust general-purpose database that fit as many application processing requirements as possible. Being a relational guy, data quality enforcement using database constraints was important, but I also wanted to leverage NoSQL's Agile development features. RDX wanted an offering that helps our customers speed application time to market. But we don't want to provide this capability at the expense of data accessibility. We want the database to be able to easily respond to queries without complex coding and storage techniques. The database needs to be able to easily answer the questions we ask. We also wanted the database to be able to leverage low-cost hardware to scale horizontally. We want to help our customers reduce database TCO. In addition, we need systems to provide high availability without increasing system complexity and cost. We wanted that solution to have 24/7 product support options. We wanted to give our customers the ability to choose from publicly supported and vendor-supported database products. Here's a quick overview of some other MongoDB features. MongoDB allows you to choose from different engines. Administrators are able to custom tailor MongoDB storage engines to fit the application's requirements. The product provides a primary key, standard single and multi-column indexes, but it also provides indexes that only contain index entries from fields that match filters contained in an expression. This allows us to create indexes with a smaller set of stored values, and that improves query performance. MongoDB provides TTL indexes. It allows you to choose the amount of time that data is stored in MongoDB. Once that time limit's reached, MongoDB deletes the data automatically. That's good for sensor data that has a limited lifetime. When we insert a value into our MongoDB database, we can check to see if it meets a set of requirements. For example, we may want a field to be mandatory. An email address is required to have an @ in the middle, and then a .com, .net, .biz, whatever we want to enforce. MongoDB also allows us to lose our primary and not be required to change the application code to point to the new primary server. The product also provides a BI connector, which allows the database to be viewed as a set of relational tables by SQL-based BI analytic platforms. That allows us to analyze data in MongoDB using standard relational database analytics products. In addition, MongoDB also provides a strong set of security features, data encryption, FIPS compliance, support for LDAP, Kerberos, and a pretty robust auditing mechanism. MongoDB stores data in JSON documents. I'll show you a document layout in an upcoming slide. The first time I saw a document being inserted into MongoDB, I was trying to find out where the document's definition was. I was trying to compare it to an Oracle table. An Oracle table definition has to be built before you begin inserting data into it. I was told by the presenter that there wasn't a definition, that the document schema is automatically created when the document is inserted. You insert the data, and MongoDB creates the schema during insertion. You don't need to predefine it. A document can be loosely compared to a row in a table. A group of related documents is a collection, and you can compare that to a relational table. The difference is, as a relational DBA, I have to pre-create that table before the developers can store data. But in MongoDB, we do not need to predefine the structure before storing data in it. It just takes what you insert and stores it accordingly. To recap, in relational databases, we have to predefine a rigid schema that has to be there before the application begins inserting data. When we alter that rigid schema, we may have to coordinate those changes with the application developers. Each row being inserted has to match the schema definition exactly. In MongoDB, you don't have to predefine the schema. It's totally dynamic. Create the schema during row insertion. Our documents' rows don't have to exactly match that rigid schema definition. Each one can be different. Here's an example. The example I use is an insurance policy application. When you call the MongoDB insert method using these specifications, it stores the information. You'll notice that our documents have some common fields at the top, but fields that differ based on the policy type. I could have stored these fields wherever I wanted to in our document, but for clarity in this presentation, I have the common fields at the top and the dynamic information at the bottom. So our common data at the top is policy number, policy type, payment information. For auto policies, we store the deductible, make, model, and VIN. For life, we store policy values, start and end date. For home policies, we store the address, deductible, type of coverage. In a relational system, because of the different attributes we need to store that are unique to the type of policy, auto, life, home, the DBA would create a separate table for each policy type. But what happens when you want a report of all the policies for a customer? And that customer happens to have a lot of different types of policies. In a relational system, we would join all those tables together to collect all the information we need. In MongoDB, we store the common information we want to search on at the beginning of our document, and then store the dynamic information that pertains to that specific policy type below it. So we can use indexes on the fields at the top to speed our searches and still be able to leverage that flexible schema. This leads to a big benefit. MongoDB's Agile schema fosters faster application development. Schema changes can go through iterations during the development process. You don't have to wait for schema changes to be made. In the next couple of slides, we're just going to dig a little bit deeper into this MongoDB architecture just to show you how it works. Let's talk about sharding for performance first. MongoDB distributes data to the different shards based on a shard key. Think of a shard as a data store, and that data store can be duplicated using a replica set to increase availability. So in our example here, we have shard 1, shard 2, and we can have as many shards as we want. The shard key is a field or a set of fields in a document that is chosen by the user. MongoDB uses the shard key to automatically distribute the data to the different shards. It load balances your data on these different shards. You select a field or a set of fields for your range key, but you don't need to hard code the upper and lower values. MongoDB automatically chooses those ranges for you and then distributes the data to the shards. MongoDB provides a balancing process which is used to keep the shards evenly balanced with data. You can also use hash keys or user-defined tags to determine how the data is divided up and stored on the different shards. The shard keys are built at the collection level, so different collections or tables can use different partitioning schemes. Since MongoDB tracks the location of documents based on the shard key, it knows which of these shards to go to when you're searching for data. So instead of scanning and searching, it knows exactly which node to go to retrieve your data. Let's move on to replica sets. Here's an example of replica sets in a multi-data center cluster. We have distributed our collections data to 3 shards for performance. Here's our 3 shards. We can now replicate the data, in this case, to 2 different sites. Each of the secondaries for our shards are in different geographic locations. In this case, different data centers. Site 2, Site 3. MongoDB replicates the changes from the primary to all the secondaries. All servers in that replica set can be assigned a voting priority and a number of votes. These settings are used during the voting process that selects which secondary is going to become the new primary in case that primary fails. The secondaries vote on which one of them should be the new primary. Since the MongoDB system itself knows which server is the primary, no application changes are required to point the application to the new primary. Once you fix that failed server, it can be added back into the replica set, either as a secondary, or it can be configured to return to its role as primary. We can now leverage the benefits of replica sets to replicate data geographically throughout the enterprise. We can store the primary servers near the applications and business units that update that data and replicate them to secondaries running at other sites. The application can read data from the secondaries but traverse our network to update data on the primary server in our replica set. In this example, we're updating data in the US and we're providing local read-only access to secondaries in the UK and Australia. MongoDB uses GridFS, commonly known as GFS, to store large data values, which include most unstructured data like videos, images, whatever. On insert, it decomposes the data into smaller chunks. When the data needs to be retrieved, it combines all those chunks together and delivers it to the requester. Since it uses pointers to the chunks, it knows where they are, so data access is pretty efficient. It also allows the application to choose where to start within the data element. For example, if you're storing a video, you could add metadata about the chunk and start processing the data by using the metadata to select your starting point. Let's talk about another NoSQL offering, Cassandra. Cassandra is a partition wide row database data store. A partition row store uses a partition key to distribute data to nodes in the cluster. Cassandra has the ability to store extremely wide rows, lots of columns, when compared to its relational and NoSQL counterparts. Cassandra's theoretical limit for the number of columns is 2 billion. Datastax, a software company that develops and supports a commercial version of Cassandra, it was founded in 2010. Their entire business model focuses on improving, selling, and providing training and product support for Cassandra. Two of Datastax's lesser-known competitors are Instacluster and WinUzone, each providing varying degrees of Cassandra support. Cassandra's claim to fame is high numbers of concurrent users, large volumes of data, ability to be easily deployed in geographically disparate environments, very fast read and write performance, and extremely high availability. You can see this by some of the businesses that use the product. Apple, 10 petabytes of data on 75,000 nodes. Netflix, 2,500 nodes running 1 trillion requests per day. Since Datastax is the most well-known Cassandra support provider, let's use them as our sample vendor. Datastax Cassandra has the ability of a single database product to seamlessly support multiple data storage models. In mid-2016, Datastax announced that its system would be able to support the graph storage model. The C-SQL language became available in Cassandra 1.1. Those that have an understanding of the SQL language will be able to understand SQL pretty easily, C-SQL. It's important to note that C-SQL does not provide specifications for join, like subquery, aggregation, and embedded arithmetic calculations. It's just not as strong as SQL. The product also provides materialized views, like its relational competitors. In upcoming slides, we'll learn more about how Cassandra replicates data to provide high availability and geographic data distribution. Cassandra also provides a tunable consistency model. It follows base, not ACID. We won't go into it too deeply. We're just going to learn about its overall capabilities. Let's take a look at this graphic. The blue line around our perimeter denotes our Cassandra cluster. Our cluster consists of 2 data centers, East Coast and West Coast. We all know what a data center is, but in Cassandra, a data center is a collection of related nodes within a cluster. It doesn't have to be a physical data center. It's a group of nodes that are related by replication and controlled by a snitch. A snitch is just a high-tech term that determines which data center a node belongs to. A node is a single instance of Cassandra. See my black arrows? Replication is used to distribute the data. The number of replicas you want to have of your data is controlled by a replication factor. That's just a number denoting how many copies of the data you want. This is really an important point. Cassandra's replication model is fully multi-master. When a node becomes unavailable, surviving members of the cluster are able to satisfy both read and write requests. In master-slave models, a single node of the group is assigned to the owner for a given piece of data, and that's the only node that's allowed to modify it. Multi-master replication allows updates to occur from any client to any node. All node members can process both read and write requests to replicated data. That's the key. All node members can process both read and write requests from replicated data. Here's a few quick terms. You control replication for your data at the key space level. You can loosely equate a key space to an Oracle schema or a SQL Server database. This provides you with a high level of granularity when determining how many replicas you want of your Cassandra data. You can see that some of the definitions are going to be familiar to relational DBAs. Tables, columns, primary keys, partition keys, clustering keys. Primary keys in Cassandra can be compared to the relational counterpart in that they have to be unique, they must contain a value. But as we'll learn later in this presentation, the primary key specifications in Cassandra also provide another functionality, like using the key to determine which node in our cluster the road is stored in. We learned in our last slide what a data center and a snitch was. In our next slide, we're going to learn what a partitioner does, as well as the gossip communications protocol when we learn how Cassandra distributes data to the nodes. Cassandra is architected as a peer-to-peer distributed system that distributes data to all nodes in the cluster. Nodes can be easily added to a Cassandra cluster to increase capacity, and failed nodes can be replaced with no downtime. Cassandra uses a masterless ring design to provide horizontal scalability. There's no concept of a master node. In Cassandra, all nodes play an identical role. Each node in the ring communicates to each other using a distributed scalable protocol called gossip. Cassandra uses the first column of the primary key is the partition key. The partition key identifies which node in the cluster will store the row. Cassandra uses a hashing algorithm called a partitioner to generate numerical tokens from each row's partition key. Cassandra uses the tokens to distribute data to the various nodes in the cluster. Each node in Cassandra is responsible for a range of tokens. The key goes into the partitioner, out comes a token, and the token tells Cassandra what node the row goes to. After the row is stored on that node, the key space's replication factor determines how many copies you're going to have. As a non-relational database, Cassandra doesn't support joins, foreign keys, and doesn't offer asset-level consistency. It is unable to guarantee total data consistency across all replicated nodes. But Cassandra extends the concept of eventual consistency by offering tunable consistency. You can tune Cassandra's consistency level per operation, or you can set it globally for a cluster or a data center. These two tables show you the different consistency levels you can choose from. There's a trade-off between operation latency and consistency. Higher consistency incurs higher latency. Lower consistency results in lower latency. The more consistent you want your data to be amongst the replicas, the bigger the impact it will have on performance. You're updating more replicas and waiting for a response. Consistency level determines the number of replicas that need to acknowledge the read and write operation success to the client application. The goal of normalization is the relational model is to store a fact in one place. The more times a fact is duplicated in the schema, the more challenging it becomes to ensure its validity. If you store a piece of data in multiple places, when you need to update it, you're going to have to update it in multiple places. You want to make sure that every instance of that fact is changed. But normalized data, depending on how complex the schema becomes, often affects query performance. When you store the fact in one place, the programs are often required to access multiple schema objects when retrieving many different but related facts. The more schema objects you have to access to store the related facts, the greater the impact it has on query performance. We normalize data, right, to reduce data anomalies, and we denormalize to improve query performance. The most common activity that occurs during denormalization is the merging of attributes that are often accessed together into a single schema object. Cassandra's goal is to provide high-speed access, right, to large volumes of data. Cassandra administrators will leverage low-cost disk storage, Cassandra's wide row features, and fast write performance to create highly denormalized models. A lot of individual fact duplication. You don't see that in the relational model. Administrators attempt to design Cassandra schemas that satisfy a query's request for data by reading as few partitions as possible, with the ultimate goal being one partition. To achieve this, they're willing to create a new table to satisfy a single query. They are, in effect, pre-building the answers to individual requests for data. Datastax manuals state that a general best practice is to have one table per query. As relational administrators, we need to be aware that Cassandra has a much different scope of implementation. Cassandra's schema design focuses primarily on query patterns. Cassandra administrators leverage the product's fast read-write performance to update the highly denormalized data. Let's talk about Redis. Redis is an open source, in-memory data structure data store. One of the more popular implementations for these in-memory systems is to use them as front ends to other databases. Those other databases are used as the persistent data store. But in Redis's case, it can be used as a persistent database, a cache, as well as a message broker. It is able to provide high performance by working with an in-memory data set. But unlike a traditional relational database buffer cache, which works by swapping old data out to make way for new, an in-memory database's strategy is to put all of the data in memory. What would we want to use Redis for? Any data store that needs to provide super fast read and write performance. You're working in memory. Streaming sensor data from a manufacturing process. Redis provides a switch that will allow you to age out older data. You can evaluate the current sensor data in real time, then aggregate that data for future analysis. Message queues, session caches, that'd be other examples. Anything that needs a high-speed cache. For retail, it would be highly personalized interactions, caching recent views of purchases, inventory and product updates, user session management and analysis, custom pricing, location-based recommendations, and of course, high-speed transaction management. For financial, once again, delivering transactions at extremely high speeds, customizing and personalizing customer offers, managing risk through fraud detection, or making analytics real time. Redis uses a key value to organize its data. Unlike early in-memory systems, it also provides built-in persistence. That means we can snapshot or journal Redis data to disk. It also offers a much wider range of data types, and it does provide node replication. Those three features may seem pretty minor, but that's what separates Redis from other in-memory offerings. Persistence to disk means you can use Redis as a real database instead of just a volatile cache. The data won't disappear on us when we restart the database, unlike many of its competitors. The additional data types are probably even more important. Key values can be a key and a simple string, but they can also be more complex types, hashes, lists, sets, and collections of non-repeating values. Redis also offers other features like built-in publish-subscribe, transactions with optimistic locking, and Lua scripting. Redis also offers horizontal scalability, auto-scaling, automatic data rebalancing during node additions. In addition, it also provides automatic node failure detection and failover, active geodata distribution, and it is fully ACID compliant. It's not base, it's ACID. It's a pretty robust product. Neo4j. It's an open source NoSQL graph database implemented in Java and Scala. The company that spawned the product was Neo Technology. Neo Technology does provide 24/7 support for licensed versions. In addition, Neo4j's enterprise versions, like most NoSQL offerings, it has many more features than its community offering counterpart. A graph is composed of two elements, a node and a relationship. A node isn't a node like we've been discussing. It isn't a server in a cluster. Each node represents an entity, a person, place, thing, category, some other piece of data, and each relationship represents how two nodes or pieces of data are associated. It's different than other databases. Unlike other databases, it's the relationships that take first priority in graph databases. This means your application doesn't have to infer data connections using things like foreign keys. The data model for a graph database is pretty simple, and it's more easily understood than those of relational and other NoSQL systems. During data analysis, we often forget that the relationships between the facts themselves can be just as important as the data elements. For intensive data relationship handling, graph databases can improve performance by an order of magnitude. With relational databases, relationship queries will incur performance issues as the number and depth of relationships increases. When you try to traverse relationships in the relational model, you end up with a lot of joins, self-joining tables together, unions, and subselects just to get to the data that we want. In contrast, graph database performance stays consistent and constant even as the data grows. On its website, Neo4j provides an example of SQL versus CSQL. CSQL is Neo4j's access language. The data they asked the developer to retrieve from two databases, one relational and one graph, was to build an org chart that was 3 levels deep. In addition to the reporting structure, they asked for additional information to be retrieved to make the query more complex. Department, geographic location. There were personnel assigned to different departments, and there were departments in different geographic locations. The code for the SQL statement was dozens of lines in length. I reviewed it, and it was not made artificially complex. The corresponding CSQL was 4 to 5 lines long. On the lower right, we see what a simple graph model looks like. The named relationships is friend of, likes, in this case a particular cuisine, serves. In this search, the cuisine we were looking for is sushi, and located in, the location of the restaurant, and for this search, that location is New York. Now we can answer that question below. Give me all the restaurants in New York that serve sushi that my friends like. Neo4j also offers fully ACID compliant transactions. We'll know the data is in there when we tell the database to make it permanent. The product also provides clustering for horizontal scalability and replication. It provides indexing, unique constraints, and other relational-like features. In addition, it provides a traditional REST API, which means it can be accessed by programming languages. It also has a JavaScript interface. You can access it using Node.js. Like most NoSQL offerings, it's designed to scale horizontally by adding additional chassis into the cluster. It also provides data replication capabilities. Here's 3 examples of how we can traverse these named relationships. In the upper left, we can leverage social relationships to make real-time recommendations to consumers. That's how eBay and Walmart uses the product. We're able to evaluate the consumer's relationships with other people, what hotel their friends stayed at, and where the consumer is going on vacation, then we can make hotel recommendations. If they ask their friends for a recommendation, it'd be the same hotel the software recommended. The middle graph model allows us to search for files. That's how Facebook and Google use the graph database model. In their cases, they use a graph data store for keyword searches. You type the keyword in, and of course you get a list of results that contain those keywords. In the past, they used simple pattern recognition to return those results. Their graph architectures allowed them to establish relationships between the keywords and the data being searched, which led to more results being returned, and the results are of much higher quality because they better match the keyword. In our example, we can look for an image that has been used in a particular movie and book. When we get that relationship match, we can then find the location on disk where that image is stored. In the upper right, master data management. Master data management, that's the practice of identifying, cleaning, storing, and governing data in the enterprise. It's data about everything: users, customers, products, employees, business units, partners. In our example, we have a graph database that stores employee hierarchy data. As we discussed previously, a graph database allows us to easily ask questions without writing complex SQL to obtain our desired results. So let's move forward with our discussion by looking at a high-level comparison of NoSQL and relational architectures. Relational DBs have a very large customer base, very large number of installations. That means you have a lot more third-party applications and tools that work with them. They also have very robust 24/7 product support. Because of their size, you don't have to worry about them going out of business. Their products are feature-rich and have a wider scope of application than the NoSQL counterparts. You can use them to solve many types of business problems. That doesn't mean they solve all of them. It means they can solve more of them than NoSQL. They can also be expensive, complex to support, and they're rather inflexible when compared to the NoSQL offerings. In addition, they don't lend themselves to easily storing non- or semi-structured data. Like I stated at the beginning of this presentation, it's hard to collectively analyze NoSQL architectures as a group because their storage architectures are so dramatically different. In general, they allow you to store structured, semi-structured, and unstructured data. They ingest pretty much everything you want to put in them. They also provide cost-effective scale-out mechanisms, easier to administer and cheaper than the relational vendor offerings. They allow you to easily distribute data throughout your data centers, whether that data center is across the city or across the country. This ability to scale sometimes comes at a cost. We learned that transaction consistency, it could be a challenge for some of the NoSQL products running on those clustered systems. The data you think may be permanent might not be. It's an instant consistency versus eventual consistency. That can be a problem. You just really need to be aware, is that NoSQL product built on base or ACID? Because they're a niche solution, they don't have wide support from third-party application and tool vendors. So we'll end our discussion with a final one-page comparison. The supposition that relational and NoSQL offerings are competitors and that they are viable replacements for each other for most implementations is erroneous. We can't easily assume that, as with most data store technologies, there will be varying degrees of overlap. Document graph, key value, wide column, and other non-structured data storage technologies, they became viable competitive offerings because they offered a solution to the business community's need to store semi and non-structured data. This rapidly expanding group of product offerings allows IT consumers to custom tailor a database architecture that meets each application's unique storage and processing requirements. We now have more choices available to us than ever before. The key to success is choosing a product that best meets the application's data storage and processing requirements. The era of the one-size-fits-all database is over. That's a very good thing for the database consumer. This wraps up our NoSQL overview. I highly recommend next month's presentation, which is going to focus on evaluating and selecting cloud DBMS architectures. We'll discuss the different types of architectures available, infrastructure as a service, database platform as a service. We'll then look at some of the more popular IaaS and DBPaaS offerings. I'll provide a set of questions each shop needs to answer to determine what is the most important to them when evaluating those cloud systems. We'll also review a starter set of criteria we can use to evaluate the various cloud alternatives. This would be a great presentation to attend. You can also send me an email to join our newsletter. Now, one of the articles in the most recent newsletter focuses on the meteoric rise of database ransomware and the growing threat of ransomware on Linux. So Kelly, do we have any questions?
Yes, Chris, we did have a few come in during the presentation, so I'll start with the first. It states, what will the future hold for NoSQL vendors, and how will they fare against their larger relational counterparts?
Well, we're all aware that the vendor with the best technology doesn't always win the battle for market share or even survive as a viable competitor for that matter. These NoSQL vendors are facing some of the IT industry's fiercest and most knowledgeable competitors. Who wants to compete with Oracle, IBM, and Microsoft? We know that these relational industry heavyweights are already attempting to co-opt the NoSQL vendor storage models. They use the term multi-model. That just means I'm going to take your storage technology, put it in my product, and I'll put you out of business. Here's a couple of examples. Oracle and Microsoft, they're improving support for NoSQL JSON documents. That's targeting MongoDB and CouchDB. Oracle and Microsoft both improving in-memory DBMS, targeting Redis. Microsoft recently unveiled a graph offering. Well, that's targeting Neo4j. Well, the NoSQL vendors themselves, they're also utilizing this multi-model strategy to gain market share. Like we learned in our presentation, Datastax Cassandra, it's a wide column data store, and now also supports the graph data storage model. In order to increase market share, the NoSQL vendors, they're going to be driven to add relational-like functionality that'll allow them to be more widely adopted. There are several NoSQL vendors that are already adding relational-like functionality. Many support asset transaction management, referential integrity, schema constraints. They're becoming more general purpose. The end result is the lines between relational and NoSQL systems they're becoming increasingly blurred. NoSQL vendor advantages won't just be their unique storage model. It will also be that they're cheaper and easier to support. That's how they're going to remain as viable offerings. Any other questions?
Yes. The next one states, is Cassandra only for large-scale implementations that have hundreds of servers?
Well, certainly Cassandra's claim to fame is very large-scale systems that can support absurdly high numbers of concurrent users, transaction rates, and very large volumes of data. You can install Cassandra on a single server if you like, but to take advantage of its performance and high availability, you need to get a quorum. You most often see shops starting with 3 servers. You can provide very fast read-write performance with a 3-node Cassandra cluster. So it doesn't really, need to have dozens or hundreds of thousands of servers. It works very well, and you can take advantage of the high availability and the performance with 3 nodes. Other questions?
Yes. The last one is, what are the drawbacks of MongoDB's flexible schemas?
Because the schemas can be very easily changed, just by inserting a document with a new specification, it requires that developers maintain a high level of knowledge and control over that schema. They've got to be very cognizant of every document schema definition. If they don't change their programs to accommodate each document schema, their application won't be able to process the data correctly. Another example, MongoDB maintains consistency at the collection. We talked about the collection kind of like a table. It maintains it at the collection level. You've got to programmatically ensure that your updates to multiple collections are processed as a single unit of work, if you want them to all go or all get rolled back. MongoDB places much more of the work on the developer. The transaction control mechanisms that we take for granted in relational systems may not be there, depending on the NoSQL product you're using. You need to be aware if your NoSQL product fully supports ACID or uses base. Any more questions?
That's it.
Okay. Well, I certainly would like to thank everybody for attending today's presentation. And as I said, that we're going to have another presentation next month that talks about the various cloud offerings. Thank you very much, everybody, and I'll see you next month. Bye-bye now.
Thank you, everyone.